In this session, I'm going to cover another algorithm, which is a machine learning algorithm. So that is naive Bayes. So as the name goes, the model is based on Bayes probability theorem. Okay. So this type of model assumes that the features are independent of each other. That is, the columns that are present, the independent variables or the independent columns that are present within a data set that are independent to each other. That is what we assume over here in naive Bayes. So it is labeled as naive because of assumption based on which the model works. Okay, so it's labeled as naive because there is an assumption that the features are independent to each other. So this model assumes that all the predictor variables are not related to each other at all. In real world, when we work with several variables, we do have some relation. Okay, hence the assumption is naive here. Okay, but there are so many use cases where we do have found this assumption to hold true. Text analysis, sentimental analysis find strong relevance of the naive-Bayes model. It is originally a classification model. Okay, so some of the use case of naive-Bayes model are it's used in spam filtering, like if let's consider an email to be checked as spam or not, that is spam filtering. So filtering the spam mails. And it is used in text classification. We will discuss on this text classification in the further classes as well. And also it is used in sentimental analysis. Okay. So these are the three areas where naive-Bayes model is used. So that is, you need to understand spam filtering, text classification, and sentimental analysis. So some of the advantages of this type of model are, since it is a probability, since it is based on probability, it is easy to follow. This type of model is very fast in very complex data sets. Okay, and this can be scalable as well. So let me go to my notes. So let me tell you the summary of that. So Bayes is a probabilistic machine learning model and is used for classification. So use cases of Bayes are spam filtering, text classification, and sentimental analysis. So text classification is like classifying document. So what does naive Bayes means? So Bayes, we already know it's based on Bayes theorem. And naive, it is assumed that the features that go into the model is independent to each other. That is, the predictor variables that are present in the model will has to be independent to each other. Okay, this is the naive assumption. That's why it is called naive Bayes. Okay. Prediction are quick in Bayes and it is scalable. So let's go to the conditional probability. So let's take an example where you have to toss a coin. So what's the probability of getting head? We know that it's 1 by 2 or zero point 0.5. What is the probability of getting tail? It's also 1 by 2 or zero point 0.5. So now let's take an example of rolls, dice. Okay, roll a dice. What is the probability that 1 comes? It is 1 by 6. What is the probability that an even number comes? Even numbers are 2, 4, and 6. So it will be 3 by 6. It is equal to 1 by 2.5. So let's take some other example of drawing a card. So probability of getting queen is how much? So we have in a deck we have 4 queen. So 4 by 52. Let's say that we have drawn a queen of spade. So now we have to find out what is the probability of spade given that queen of spade is drawn. So we know that there are 13 spade cards in the pack of deck of 52 cards. So in which we have already taken out queen from that. So remaining 12 cards out of that is 12 by 51 because we have already taken one card. So we have already seen Bayes theorem that P of A. So we have seen that P of A by given B is P of A intersection B by P of B. But Bayes theorem says that P of Y given X is P of X given Y into P of Y divided by P of X. So this is conditional probability. So let's look at this only. So now let's say P of Y given x1, x2, x3, so on, xn is equal to p of x. So let's say p of y is equal to k. We have to find out that p of y at k, where given x1, x2, x3, so on, xn is equal to p of probability of x1 given y is equal to k, the probability of x2 given y is equal to k, and so on till probability of xn given y equal to k into probability of y equal to k. You just have to substitute y equal to k over here, and x it goes from x1 till xn. So similarly, what happens here is probability x is there. So we had taken x. So for x1 till xn, we have to take probability of x1 till given y. So probability x2 given y. So still xn we have to multiply, and then we have to probably multiply probability of y at point k. Then divide by p of x is p of x1 into p of x2 into p of x3, so on p of x. So now let's take an example that, so just forget about this one. So what's happening here is that, so so we have uh, four fruits. Okay, we have banana, orange, and other fruits. Okay, so total we have 1,000 fruits in our data set. Let's consider. So 500 of them are banana, 300 of them are oranges, and 200 of them are other fruits. Okay. So now let's say what is how many bananas are long. So out of 500, we have 400 bananas long and 100 bananas not long. So how many bananas are sweet? So we have, let's say we have 350 bananas sweet. So 500 minus 350, 150 bananas not so sweet. So now how many yellow color bananas are there? So we see that we have 450 yellow color banana, and how many are there total? 500. So 450 minus 500 minus 450, 50. So 50 not yellow banana are there. So now we'll see oranges. Okay. So we have 500 bananas in total. So we write 500 over here in total. So now we see oranges. So we have, let's say we have zero oranges that are long. Okay, oranges are long. So we have here zero. So zero oranges are long. Not long is 300 is total oranges. So 300 will be not long. Now, how many are sweet? Sweet oranges, let's consider. So sweet is 150. So how many are there in total? 300. So 150 are not sweet as well. And how many are not yellow oranges? So oranges that are almost all are 300 of them are yellow. Orange is yellow and not yellow is zero. So total oranges is obviously 300. So now let's say similarly long. How many other fruits are long? 100. So remaining fruits are total out of 200. We have 100 not long fruits. And how many are sweet? So we have 150. So total how many? 200, 200 minus 150, 50 are not sweet. Similarly, yellow is 50 and not yellow is 150. So we have these many, a banana, orange, and so we have total 200 other fruits. And now you have this tabular column. So total number of fruits is 500 plus 300 plus 200,000. Okay. So now what is the probability of banana? So here probability of y is, we have mentioned y is equal to banana. Okay. So we are mentioning here probability of y is equal to k, right? Here instead of probability of y is equal to k, we have banana. Y is banana. But probability of banana is, so how many bananas are there? 500. And how many total fruits are there? 1,000. 500 by 1,000, 0.5. So probability of orange is, orange how many? 300. Total 1,000. 300 by 1,000. Similarly for others, how many are there? 200 by 1,000. Okay. So long, probability of long. Okay. Probability of how many are long? So we have to see probability of long. So total long fruits long are 400, right? So how many are long? Let me check. 400, right? So sorry for 500. So 400 plus 100, 500. 500 by 1,000 is 0.5. So how many are sweet? Sweet is 350 plus here total is 650, right? 650 by 1,000 is 0.65 is sweet. So similarly, yellow is 800 over here. So 800 by 1000 is 0.8. So probability of long given banana. Probability of long given its banana. So how many of them are there? So probability of long given banana. So 400 by 1000, right? 400 by 500. Why 500? We are taking only banana, right? So total bananas is 500 and long are 400 only. So probability of sweet given banana, probability of sweet given banana 350 by 500. Probability of yellow given banana is 450 by 500. Similarly, probability of long given orange. So our long is 0, given orange is total 300, 0 by 300. Probability of sweet given orange 150 by 300, 0.5. Probability of yellow given orange is 300 divided by 301. So similarly, probability of long given others is 100 by 200.5. Probability of sweet given other is 150 by 200. And similarly for other, probability of yellow given other, which is probability of yellow given other is 50 by 200. Is 1 by 4.25. So now we have to find probability of y is equal to banana given that the fruit is long, sweet, and yellow. Okay. So P of y is equal to k, where probability of y is equal to banana, where x is long, sweet, and yellow. So what is the formula for this? So probability of long given banana, probability of sweet given banana, probability of yellow given banana into probability of banana. Correct? Divided by probability of long, probability of sweet, probability of yellow. So substitute those answers. So let's see the probability of long given banana. Probability of long given banana is here we have 0.8. Probability of sweet given banana 0.7. Probability of yellow given banana 0.9. 0.8 into 0.7 into 0.9. 0.8 into 0.7 into 0.9 into, so probability of banana is 0.5 divided by probability of long sweet yellow. Probability of long 0.5, 0.65, 0.8. Okay. Divide it and you will get the answer of 0.9. So we have 97% of chance that a fruit which is long, sweet, and yellow is a banana. So highest one is class is selected. Okay. So when you say that probability of a fruit being long, sweet, and yellow, so then we get that it is a banana. That is probability of banana being long, sweet, and yellow is 97%. Similarly, let's look at probability of orange being long, sweet, and yellow. Probability of orange being long, sweet, and yellow is probability of long given orange. Okay. Probability of, we have to take probability of orange given long, sweet, yellow is probability of long given orange. Probability of long given orange is how much? 0. So whole numerator will become 0 because we have probability of long given orange as 0. So it is 0, so it will equate it to full will be equated to 0. Now the other is P of others given long sweet yellow is probability of long given others, probability of sweet given others into probability of yellow given others into probability of yellow. So let's see probability of long given others is 0.5 into 0.75 into 0.25 to 0.2. Probability of long is 0.2. Probability of others is 0.2 divided by probability of long into probability of synthesis. So 0.5 into 0.65 into 0.8. Okay. So we get it as 0.0707 or we have 7.2% of them are other fruits. Okay. So we have 97% of them being banana, long, sweet, and yellow, and 7.2% of the other fruits being long, sweet, and yellow. Okay. Similarly, what we can do is that this will get equated to 0. So we can take care of this by making this value as 1. Okay, we can make this value as 1 so that we will get some value over here. Let's see that how we can do it. So the problem of zero frequency, the drawbacks of this base is the problem of zero frequency. So this is the zero frequency. Because of this, the value in the numerator tends is equated to zero, whole value be considered as zero. So this will be a problem. So the problem of zero frequency. If you look at p of x given y, it turns out to be zero. This will be class probability zero. So this is one of the flaws of naive-Bayes theorem. In order to address this flaw, naive-Bayes uses Laplace correction. So that's what we are going to discuss. So here Laplace correction where p of long given orange is equated to zero and hence overall probability becomes zero. What we can do is that to avoid this, the increase the count of variable from 0 to 1. So increase this count of variable to 0 to 1 so that overall probability is non-zero. This is the Laplace correction we have to make. So replace 0 by 1 in the entire table so that some idea about the probability of each class can be obtained. This goes internally in the algorithm. Accordingly, the probability of each class is evaluated. So now let's see the problem with the correlation part. So the problem with the correlation. So what will happen if independent variables are correlated or the predictors are correlated to each other? If there are any correlated predictor variables, it is important to remove such variables or merge such feature so that the assumption of Bayes is valid. Since our assumption says that in Bayes, we don't need to have predictor variables related to each other. So we have to make sure that we have to remove one of the variables or merge two variables such that only one time the value is taken for consideration variable. So twice it is not considered okay for assumption. Okay, so we have to merge such features so that assumption of neighbors is valid. So this was all about it. So what are the classifiers of naive-Bayes algorithm? So let's see from here first. So what is classifier says? If a target variable is continuous, then Gaussian classifier is used. If a target variable is more than two classes, then a multinomial classifier is used. If a target variable has only two classes, then binomial classifier is used. Similarly, same, okay? Instead of that, we can say Gaussian is used. A Gaussian assumes that the features follow normal distribution. Multinomial useful when your features are discrete and useful. Bernoulli says when your features are binary in nature. So what are the cons of this? Okay, let's see the cons. Okay, so that I have already discussed. Okay, cons. We the cons is we need to remove the correlated features because they are voted twice. Okay, that's what I was saying. If there is two variables that are correlated, we need to remove one of them or do merging of both variables. Otherwise, there is a problem with our naive Bayes model. So required to remove correlated features. Okay, then zero frequency, as I already told. So if one of the uh, values say, tends to zero, then whole probability becomes zero. So that is a zero frequency or zero probability. So we can deal with this using Laplace correction, where we have to avoid this. We increase the count by from zero to small value like one, or other smoothing techniques we can use. So till here I have all discussed all the theoretical parts that are required for solving the Naive model or knowing the Naive model. So I will do the coding part in the next class where we will build a Naive model for prediction of uh, output class in our data set, which is obviously we are going to take a classification data set. So thank you for attending the session. Hope you understood everything I taught in this session.